Hey everyone, and welcome to my talk about monitoring Kubernetes and choosing the right metrics for incident alerting. I hope you're having a good time at the conference so far and that you take away something valuable from my talk as well. So, a quick introduction to break the ice. I'm Shubham and I'm a developer relations engineer at Zenduty. It's an advanced incident management and response orchestration platform. I call myself an expert in making mistakes, learning from them, and advocating for best practices for org setting up their DevOps, SRE, and production engineering teams. So, the burning question, what is this talk about? So, we'll start by introducing the right metrics to monitor Alert Manager. We'll play around with some metric algebra to formulate statistics that matter to you personally. Then we'll move on to learning from the mistakes made by veterans in our industry. A quick primer on what to do and what not to do. We'll briefly touch on anomaly detection, whether your system could be benefiting from proactive alerting. And finally, the kicker is bad monitoring costing you and why you should care. So, this must be familiar to a few of you. I was once told by a colleague of mine that Prometheus can be too prompt for its own good. If you don't rein it in, you're going to have a dedicated Slack channel full of hundreds of alerts every couple of days. And that's because building an efficient and battle tested monitoring platform takes time. You need to burn your fingers a little, learn the ropes before you build a monitoring system worth something. But there are some things that you can keep in mind on day one. Firstly, your alert should be based on impactful symptoms. You shouldn't be getting alerts in the middle of the night for alerts that really don't have any business impact to your org and can be dealt with later. If an unexpected value in a metric doesn't have appreciable impact, it should not be an alert. You can check those values and generate maintenance tasks, but don't wake anybody up in the middle of the night. Secondly, your alert should be actionable. If you're getting woken up, your alert should at least be about an occurrence that you can do something about. Nobody wants to keep looking at an alert completely dazed, wondering whether what it's about and what they should be doing. And finally, your alert should be concise, accurate, and minimal. Simple as that. And so now to the meat of the talk, learning from mistakes. We'll be going through some existing metric monitoring and alarms set by companies in production, what they're missing out on, and some fun with algebra. So the biggest mistake we've seen people do is not alerting at all. It's a no-brainer, but we got to start somewhere. You see so many companies not setting up alerting at all. They have teams with multiple shifts just staring at those graphs and dashboards all day long, waiting for something to cross that dotted red line, and it's just really sad. Now we have not enough alerts. They say half knowledge is fatal. Well, so is an inadequate number of alerts, and you're leaving out critical metrics in that case. This could lead to situations where you're doing guesswork based on improper assumptions, and the business impact to those actions could be exceedingly incremental. And finally, we have not setting the right alerts. This could be setting up excessive alerts, mislabeled alerts, or monitoring metrics that just don't matter. And proper and adequate alerting should allow your team to correlate performance issues and outages with code changes, infrastructure instabilities, or just unmonitored blunders. So firstly, we have Nginx too many 400s. So what this alarm does, it monitors the number of 4xx requests received in 1 minute and fires notifications when that is more than 60% of all requests. What's right about it is, firstly, keeping a track of 4xx requests is a welcome behavior. And secondly, you're only generating warnings and not an incident. But what's wrong about this is you're also counting the HTTP 4229 requests, that is the requests that are falling outside the rate limit. And this would basically cause this alarm to be triggered very frequently. We correct this by simply changing the equation to disregard the requests outside the rate limit, and as simple as that. But after this update, we found that the noise to signal ratio for this particular alarm was 18 to 82%. So that means that only 18% of the alarm alerts ever triggered by this alarm were legitimate. And that's just a mind-blowing number for me. Now we have host context switching. So this alarm monitors the number of times your node switched context in a period of 5 minutes, and it fires a notification when the figure exceeded 5,000. And we have a few suggestions for this. So firstly, if the property is too high constantly, you should switch to a memory or RAM optimized instance instead of keeping the current configuration for longer. And that's because context switching is not recommended for mature products at all. It's only for teams still in R&D phases establishing their benchmarks. And if your performance is on par with the usual benchmark constantly, you can run this much less frequently than 5 minutes, like maybe 30 minutes to reduce the noise. But if you don't monitor this metric at all, you would not know why your operations are choked up. Now we have HP at max capacity. And what this alarm does is it fires a notification when the answer to maximum possible replicas minus current replicas is 0. So what's right about this alarm? Well, almost nothing. Why? That's because when the alert will be triggered, the system is already at max capacity, the thieves have escaped, something is bound to be broken or at least break later, and the alarm will deliver alerts too late to prevent a major incident. So the correction here is just making sure that you get an alert at 80% of max capacity so that your team still has some time to scale effectively or diagnose why there's a spike in the first place. HP is scaling limited. So this alarm notifies your team when the number of pods decreases below a certain threshold. And what's right about this is that some teams run the risk of a pod shutting down physically. And this alert may be a basic saving grace to them to at least get notified when there's a failure like that. But what's wrong about this is it'll also fire alerts on the pods hit minimum threshold capacity, and it'll be a constant source of noise for well-scaled systems. Some more examples on what to do. Some of these may be a little basic. Starting with Prometheus replica down. If your replicas are below certain limits, you should get alerted and at least understand why you're facing that scale. A no-brainer, but sometimes due to name changes or config file errors, your Prometheus may be disconnected with the alert manager. A basic alarm like this could potentially save you from some embarrassment down the road. We have container CPU usage. So just like HPS scaling limits that we discussed earlier, container CPU usage can also be monitored with reasonable thresholds based on benchmarks and approximate response times. And sometimes we rely too much on automation and forget that we need to track these auto restarts as well. It's a basic alarm which is missed sometimes, but could surely help correlate other service changes and delays. This one detects when an unsupported node is attached to your cluster, and it could lead to situations where your structure might not work as intended, and it's hard to diagnose without an alarm like the above. This is an alarm notifying when pods are killed due to out of memory issue, pretty basic. This one is very similar to the 400s example we looked at earlier. This one detects when there are too many requests being written with a 5x6 response code, and it can help correlate system or code changes to drop requests. A friendly reminder that your engineers should also be tracking Nginx configurations and getting alerted before your network interface reaches its capacity levels. Tracking what your Prometheus is scraping is highly suggested, because if your Prometheus instance is scraping too much data and goes out of memory, it could go down or frequently restart and delay alerting very sequentially. And you should always be logging your P50, P90, P99 latencies, allowing your team to correlate an increase in latency with external causes like incidents, new feature pushes, or maybe even marketing campaigns causing an increase in traffic. And now we move on to something a little more advanced, being proactive with Prometheus alerting and putting some light on anomaly detection. So we stumbled upon some research by a few good folks at GitLab and decided to give a swing at it ourselves. So the following serves as a case study of sorts about our implementation of anomaly detection. So why is anomaly detection useful? Firstly, just for diagnosing incidents, you can lower the average amount of time it takes to discover an incident, immediately identifying which services are operating outside its regular bounds. Detecting application performance regressions. If an n+1 regression is introduced and leads to one service calling another, you can quickly track down the issue and resolve it. Identify and resolve abuse. So you can get protected from a small subset of users that could be trying to take advantage of your free services. And most importantly, security. Anomaly detection allows you to spot unusual trends. So some of the primary principles of statistics can be applied to detecting anomalies with Prometheus. But first, your time series data must be aggregated correctly. So we use a standard counter of HTTP total requests as the data source for this demonstration, although many other metrics can be applied using the same techniques. So the z-score is measured in the number of standard deviations from the mean. So a z-score of 0 would mean the z-score is identical to the mean in a aggregated time series data set. So assuming that the underlying data has a normal distribution, 99.7% of the samples should have a z-score between 0 to 3. So the further the z-score is from 0, the less likely it is to exist, and we will be applying this property to detect anomalies in our Prometheus series. So how do we calculate the z-score anyway? Firstly, we calculate the average and standard deviation for the metric using data with a large sample size. So for this example, we're using 1 day's worth of data. And to get that, we firstly take the long-term average value for the series with the following expression. This is the average over time of HTTP controller requests, the metric that we are monitoring over a period of 1 day. Then we take the long-term standard deviation for the series with the following expression. And then once we have this, we can calculate the z-score for the Prometheus query once we have the previous ones. And to do that, we get this one. For a more detailed guide, check out the blog by GitLab about z-score from 2019. It's a standard primer about everything z-score, and I'm sure it will help you in your journey. And once we were done, we could presume that any result that is outside of the range of +5 to -5 for us is an anomaly based on the statistical principles of normal distribution. So this idea can serve as the foundation for proactive alerting. And we made a big leap by assuming that our underlying aggregation has a normal distribution, and metrics that don't have a normal distributions include things like error rates, latencies, skew lengths, and for them our results may be skewed, but they tend to work better with fixed thresholds for alerting anyway. And for those metrics, do check out seasonality again by GitLab. Now z-score live in action. So z-score helped us identify an anomaly where we were sending fewer than expected alert SMSs every hour. So turns out a recent code change was causing the third person on an escalation cycle to not get an SMS and directly get a phone call instead. And not only did z-score help us detect this error in just a few hours, but it saved a few of our users from some ringing confusion and us from those expensive call costs. But why correct our math at all? Why do so much for just alerts? Except some hassle to a few employees, it's not costing us anything, right? But well, that's where it gets interesting. So the following are going to be conservative estimates, not accounting for storage costs, VPN, and other cloud add-on costs. So the final figure could be much higher. So the bandwidth cost per GB per NAT is around $0.045. The NATs required for a minimum of 2 regions is 6. We're assuming a company in a mine with 500 employees, around 70 people in the senior engineering, DevOps, SRE umbrella, and only 30 of these people are ingesting all of this data. And on an average, everyone's getting around 20 GB of monitoring data ingested every day. And scaling this up for a period of 1 year, you get a figure around 60 grand. And that's not a very ignorable figure now, is it? And now how much can you save with proper alerting? With well-configured alerting and metric monitoring, not only is your Prometheus scraping only relevant data, but your team is also spending much lesser time manually monitoring performance and just relying on intelligently set reliable alerts to let them know when something has gone wrong. So according to our data, on average, a team can save up to 35 to 45% of the previously calculated expenditure with the right metrics and alerts. And great, you will now only be generating alerts that require attention. But how are you going to approach incident management here for cleaner resolution? So a good alerting structure is definitely a must for quick resolution, but make sure that you don't lose the war against time during firefights due to human errors or miscommunications, and assess whether your organization could need an updated incident response tooling that keeps responders on the same page, harnesses context-rich data from your observability plane, and enables your team to jump back from issues as fast as they can. And yeah, that's it. That was all my time. Thanks for listening. I hope that you have a good time at the conference later. If you have any questions, feel free to reach out to me on LinkedIn or Twitter. And yeah, thanks for joining in.